The lecture today is going to cover section 5.5, where we're going to do counting techniques. We're only doing the first three subsections of 5.5, and then we'll go on to 5.7, which is the summary of it all. So let's get going. 5.5 is about counting techniques, and there's different ways you do some counts, and we'll cover all three important ways that you think about counting different groups and different subgroups. The first one is, let me see if I can move this. Okay. Okay. The first one is just the straight multiplication rule. And this is pretty straightforward. This is if you have a list of things to choose from. So the one classic example of, choices in a row that are sequential is sometimes restaurants do this, where you have a choice in a fixed price dinner of appetizer, entree, or dessert. In this example, you have two choices for appetizer, and you also have four choices for entree: chicken, beef patty, liver, and roast beef. And then you have two choices for dessert. So you can imagine how this might look if you were going to sort of get a list of all possible choices. So the question was, how many different meals can be ordered? Choice of two, choice of four, choice of two. So you can sort of see two, four, two are the order of choices. And it turns out when you consider the full list of choices, you can do it by brute force here. So each appetizer here, you get a choice of two, super salad, and then with whatever appetizer you chose, you get a choice of four different entrees and then a dessert. So this tree here shows you the total different ways you can, have a meal. The counting of all possible meals, it can be done by a tree. And it's two times four times two, the number of choices at each step. So you may be given a problem like this where you're sort of just laid out choices in a row. Okay. And this is the process of doing it. Just the multiplication straight through to get the full count of all possible choices. Okay. So that's one method. And this is the rule here, the multiplication rule of counting is if your task consists of a sequence of choices where there are P selections, Q selections in the second choice, R, and so on, you just multiply them out, and that's the total number of choices possible. We're going to cover two other cases where you're not going to just do a straight multiplication through of choices. It's going to be worded differently, and you'll see the difference. But in this case, task consists of just a sequence of choices, and you know the number of choices at each step, at each choice, and you can just multiply them out to get the full count of the different ways of putting them all together. So here's another one, the IATA, which is the group that assigns the three-letter codes that represent airports. Um, how many airport codes are possible if you have three letters in a row and you have 26 to choose from? Well, by the multiplication rule, it would be 26 to the third power, 26 times 26 times 26, which is 17,576. So that's how you'd get the total number of airport codes, again, using the multiplication rule. But now let's move on to how we count without repetition. Okay, so this is the case different than the previous cases where you have a pool to choose from. In this case, the example here is a 14-member committee of people, and you need to choose a chair, a vice chair, and a secretary. Okay, but the first person selected would be the chair, but they can't be rechosen as the as the vice chair or secretary, right? So once you choose the chair, this is the idea of without repetition. Once you choose the chair from the 14 people, you only have 13 people left to choose the vice chair, and then 12 left to choose the secretary. So in this case, counting goes from 14 to 13 to 12 uh, possible. So in the multiplication rule, this is what it would look like. 14 for the first choice, 13 for the second choice, and 12 for the third choice. Again, this, unlike the airport three-letter code example, this is without repetition. You can't repeat uh, the choice after you've chosen it. So in this case, 14-member committee of people choosing the chair, vice chair, secretary. You can do it 2,184 different ways. So keep that in mind. The key here is whether the example talks about repetition or not. In other words, can you repeat the choices or not? So for the example, in the airport code example, you could repeat the choices. So moving on, this is defining a new concept for some people. The factorial symbol is this one here, and it very much relates to our example of the committee selection, a 14-member committee, chair, vice chair, and secretary. The best way to calculate it is the factorial symbol, right? So if you went all the way down to one, this is what the symbol means mathematically. If you see a number, any number greater than or equal to zero, any integer greater than or equal to zero, and you see the exclamation point afterward, that means factorial. And the way you define that out here is n factorial is n, that integer, multiplied by n minus 1, which in the previous case was 14. Then this would be 13, and you would keep doing such until you went all the way down to 1. That's what n factorial means, all right? So we didn't do n factorial in the previous example. We only chose 3 officers. So we didn't go all the way down to 1, but n factorial means go all the way to 1. Special case, you should always keep this in mind, the special case of 0 factorial, 0, remember, if the n has got to be greater than or equal to 0, 0 factorial equals 1, as does 1 factorial equal 1. So these are equivalent at the very end of the factorial sequence. Okay, so if you haven't seen this symbol, you'll see it for the rest of this lecture and when we discuss counting techniques. So that's what a factorial symbol means. So now we are going to do something similar to our earlier examples, but you're a book representative and you have to go to 7 different campuses to talk to people on each of those campuses in your day travel. How many different ways can you drive your car between the 7 campuses? Well, the way it would work is at the beginning, you've got a choice of 7 campuses to visit. But once you visited that first one, you have 6 left to choose from. So again, this is ripe for a factorial notation. And since you have to visit all 7, unlike the committee example, where you had to just choose 3 officers, in this case, you have to visit all the campuses. So you would go all the way down to the last campus in that day. So this is what it would look like. It would look like 7 campuses, first choice, 6 campuses, second choice, 5 the next, 4, 3, 2, 1. So you'd have all those choices, and that is by definition, 7 factorial is this sequence of multiplication. So if you were a book representative and you had to travel to 7 campuses, you would have 5,040 different routes. Okay. That would be the different routes you could choose from during that day. So that's an example of how to use a factorial in a counting problem. And this counting problem just says 7 choices, have to visit them all. What different routes can you navigate the 7? That would be 7 factorial. Okay. But we have different ways to consider these things. We we also can solve counting problems using permutations. And we also can talk about combinations. The last two parts of this 5.5 section we're going to talk about are permutations and combinations. So here's the definition of permutation. And the key thing is underlined here. Repetition is not allowed. So the way we say this, a permutation is an ordered arrangement, okay, which R objects are chosen from n distinct different objects. So, and R always has to be less than or equal to n by definition. And repetition is not allowed. Okay, you can't repeat things. So this is the symbol for permutations. When you see something of this symbol, the subscripts are before and after the capital P. What you're talking about is the mathematical representation for calculating the permutations of a given scenario. So the symbol N subscript capital P R subscript represents the number of permutations of R objects selected from N objects where repetition is not allowed. So that's its definition. Again, uh, here's what we would do. We'd have to make sure there are N objects are distinct. Okay, we have to make sure they're distinct and different. So the full set is different. It's no repeats in there. And when you chose an object, when up to the R objects that you're going to choose, repetition is not allowed. You're not allowed to repeat a chosen distinct object in the N objects that are out there. But the key here is order is important. This is what's going to separate out permutations from combinations is order. So the way we calculate the number of permutations of n distinct objects taken from R at a time is this formula here, and it takes advantage of the factorial symbol. So this number of permutations of n distinct objects taken R at a time is n factorial divided by n minus R factorial. Okay, so that's the formula we're going to use for permutations. But remember this, order is important, and you're going to use that as the distinguishing characteristic between permutations and combinations, which we'll get to in a second. Let's do an example, okay? Let's just evaluate these, okay? By hand, I can calculate this. Remember, uh, this is how we say this, okay? Back here, if I want to take n distinct objects, take an R at a time, I would do these different formula here. So n distinct objects take an R at a time. There's 7 distinct objects. We want to take 5 in example A. In this case, we want to choose all 5 of 5. Okay, so that's what that would be. How would we do this? We type everything in the formula. Okay, so here's the formula, 7 distinct objects taken 5 at a time. Okay, right here. That's the formula of that. That's the phrasing of the permutation. And it's 7 factorial divided by 7 minus 5 factorial, which is 2 factorial. And one thing, we remember what 7 factorial is. It's 7, 6, 5, 4, 3, and 2 factorial. 1 factorial is 1. We defined that earlier, so we don't include it here. But we can factor out the 2 factorial because that was in the denominator here, standard rules. So this is our answer. The ways to choose 5 in 7 distinct objects, how we can choose 5. Okay, so that answer is 5 right here. 2520 ways to do that. Okay. If we want to evaluate the second one by hand, this permutation calculation, we'd put it together here. Okay. And we remember what 0 factorial is. That's always 1. So 5 factorial is only 120. So you can, this is sort of will be a rule of thumb. If you, the way to choose five things in five different ways is going to be this calculation of permutation. It's no different than what we saw earlier, which was the routes of the book salesperson who had to run around seven different places. Okay, so this is these are examples of how to do this calculation of permutations. Okay, so let's do another example. Betting on the trifecta. If you know about if you know the horse racing, you may know what this is. But in how many ways can horses in a 10 horse race finish first, second, and third? And if you think about this, you could probably noodle it out, but you can't always figure it out. All right, remember, after we chose the first horse, it can't repeat and be the second horse or the third horse. So that's why it's permutations. And order is important. Okay, so without replacement, and order is important. So 10 horses are distinct. That's part of the definition of permutation. Once a horse crosses the finish line, that horse is out of the choice of other horses to finish second. So finishing order is important here. So it's a permutation, how to take 10 a permutation of 10 distinct objects taken three at a time, first, second, and third. So this is the definition of a permutation, and order is important. Okay, so here's how we would do that calculation of the permutation for horse finishes. 10 factorial divided by 10 minus 3 factorial, which is 7 factorial. We can reduce this here by eliminating 7 factorial in our calculations. We have 10 times 9 times 8, 720 ways. So that's an example of how to calculate permutations in a word problem. If I gave you a word problem just like this, in how many ways can horses in a 10 horse race finish first, second, and third? So I hope that helps. Now on to combinations. We just have to understand the difference. Combinations are similar to permutations, okay? And when I read this, you may hear the similarity. A combination is a collection, without regard to order, of R objects chosen from N distinct objects. And that looks very similar to what we defined as permutations. Okay, R is always less than or equal to N, and it's without repetition, okay? Without repeating everything. Okay, so understand the symbol CNR is different than PNR, permutations and combinations. So try to understand this as best you can as you do the homework and study. So here's a way we can do this. We have four people are going to go play golf, okay? And they want to select two players from each. This all possible combinations, not permutations, but combinations, okay? And another way to say that is in a list of distinct four, the four players, how do we make pairs? Choose two of the four. That's what combinations is. And for this small a sample, we could just do brute force. We could just lay them all out. It's Roger Ken, Roger Tom, Roger J, and we just see there's six. But so this is the answer. We know the answer of the combinations is total number of combinations possible is six. And we just did that by brute force, just by listing them, which is what this says up here. Just list the combinations. But how do we calculate the combinations? Well, we have a new formula for combinations. And the important part here is order is not important. The way to distinguish combinations is order is not important versus permutations where order is important. First, second, third. Okay. That's where order becomes important in the horse race example. So we have a new formula here. We've added the R factorial piece to our calculation of combinations versus permutations. Okay, looks similar to permutation calculation, but remember, since order is not important, it doesn't matter who's first, second, or third. We actually change the formula and divide by R. Let's go through some examples. Uh, the four distinct objects choosing one where order is not important. Six distinct objects choosing four where order is not important. Six distinct objects choosing two where order is not important. Let's go through it. Just do it by straight calculation. And this is remember, the formula is here. That's the formula we're going to use. So here it is, four distinct objects choosing one. Well, here's the formula. It's 4 factorial from n, which is the left side of the C symbol, and 4 minus 1 is 3 factorial. We also have the right side represented here as r factorial on the in the denominator. So this is 1, this is 3 factorial, this is 4 factorial. And you can sort of see that these eliminate 3 factorial, 3 factorial, eliminate with each other. We're just left with 4. But again, just think of the logic. How many ways can I choose one where order's not important from a group of 4 distinct objects? Well, I can choose just one and just one each 4 times. So this should make some logical sense that the answer should be 4. Okay, but what about the second example here? 6 distinct objects, how to choose 4 where order does not matter. Well, we just plug it in the formula, and you can see how things get reduced. It's 6 times 5 times 4 factorials. They get crossed out. You have 2 left. So that's 30 divided by 2. So that's 15. You can choose 15 different where order doesn't matter, distinct
Professor,
groupings of 4 from 6.
Professor.
Okay, so then we could do the from a distinct group of 6. How can we choose 2 where order is not important? We get the same answer here. I have some question in the chat. You can just ask away, Celine. That's no problem.
Okay, so for the numbers after,
I don't think I can hear you. Why? Why is that? I'm sorry. Can you try again, Celine?
hello, can you hear me?
Yeah, I don't know what I cannot hear you, unfortunately. I don't know what my settings are for that. Maybe if you if it's short, just could you type it in quickly to the chat? That would be the best way to answer it right now. Sorry about that. I'll continue on and wait for Celine's question and get back to that. So that's combinations and permutations. They're different. Let me give you an example. Oh, here's the question. Yes. So in both formulas for combinations and the question by Celine was, is the number in the numerator just the numbers followed by the numbers before C? I think what you're asking is when you look at this formula here that I'm circling with my cursor, okay? When you look at the symbol for the form to calculate combinations, to the left of the symbol is N. And that's the full number of distinct items you're going to be choosing something from. Remember, this is a choosing problem. So that always will be in the numerator for both permutations and combinations. But when you get to combinations, it's a different formula. Both permutations and combinations have n minus r factorial in the denominator. But combinations, because order doesn't matter, will also have r factorial in the denominator here. Okay, so it's a little different. Let me get to these other questions. So the one question is, how do we know whether it's a combination or a permutation? Combination is where order of the selection of the R objects does not matter. When it does not matter, we can use combinations. But if it does matter, in the case of permutations, it matters where we say things like first place is different than sec place is different than third. So order actually makes a difference there, first, second, or third. That's where order matters, and that's when you do permutations. Okay. So the other question was C doesn't include the number three. Yeah, I'm not understanding the question. So let me just show you again. If we're doing combinations, okay, what you're saying is you have n distinct items. How many ways can you combine R items from that n, a number n distinct items, where order does not matter? You could just choose the order, could be any, front to back, back to front, doesn't matter. Um, Question C, I still don't know where three comes in. Question C is six distinct items, how to choose any two where order doesn't matter. Okay, so I have six distinct items. How can I choose any two of them where order doesn't matter, first or second, second, it does not matter. So I just plug the six and the two into these slots here for n and r in the formula. And I get 6 factorial divided by 4 factorial, which is 6 minus 2 factorial. And then the denominator also includes r factorial. R in this case for C is number 2. Okay, so I'm trying. Yeah. Oh, so you're saying, well, remember, 4 factorial, that's a good question. So the question was, um, in question C, isn't 6 factorial 6 times 5 times 4 times 3 times 2 times 1? Yes. But 4 factorial and 4 factorial are the same. So for ease of calculation, what we do when we have this construct here, we know 6 times 5 times 4 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1. 6 factorial includes 6 times 5, and then we replace the last step with 4 factorial. And we do that for convenience to be able to cross this out. So 4 factorial is 4 times 3 times 2 times 1. And we just cancel that out with the other 4 factorial here. So that we're just taking a shortcut instead of, describing it all the way out. Yes, Ayla answers the question for us. Okay, good. All right, let's move on. So let's do another word problem example of a combinations problem. How many different simple random samples of size 4 can be obtained from a population of size 20? And we don't care, and there's no indication here that order matters. This is not like first place, second place, third place, or chairman, vice chairman, secretary. So we can use combinations here as opposed to permutations, because it doesn't matter of the 4 and the sample size. The order doesn't matter. We just want 4, right? So that's one of the distinguishing characteristics. So we're going to use formula 2, which is combinations, where n is 20 and r is 4. Here is the formula, okay, right there. N is 20, r is 4. Here's 20 factorial. And again, we use the the easy solution here is to cancel out 16 factorial in both. 20 minus 4 factorial is 16 factorial, so that we can take advantage of this. We know we're going to eliminate this. And now it's 29 times 19 times 18 times 17 divided by 4 factorial. 4 times 3 times 2 times 1. And then after the elimination of 16 factorial, we can put it in a calculator and get 4845. There are 4845 different simple random samples of size 4 from a population whose size is 20. Again, we took advantage of where the order doesn't matter. As soon as the order matters, we got to go to permutation. Okay. So this is the summary. We solved counting problems using permutations and combinations. And here's the definition. A permutation refers to the number of ways to arrange a set of items where order matters, while a combination refers to the number of ways to select a group of items from a set where order doesn't matter. Okay, so essentially what we think of as a permutation is an ordered, because order matters in a permutation. Permutation is just an ordered combination. Okay. Combination doesn't consider their position or their order at all. Okay. So that's summarizing how we do counting with combinations and permutations. Any questions? Okay. We didn't do this last section. This is the summary table. Combinations, permutations, and this right here where order doesn't matter. Okay, when order does matter, we're going to use the permutation formula. And if we have replacement, then we can just do these kind of things. And that's where we did, remember the airport codes example. We could reuse from 26 letters, we could reuse the letter in our second choice. Okay. So in a 3-letter combination, we could reuse the letters, and that's why we just went N to R. Okay. From a list of N distinct items for the airport code, okay, we had 26 letters to choose from, 26 distinct letters to choose from. How can we choose 3? That's 26 to the third power, because we could replace it and choose it again. Okay. It without replacement, it'd be a permutation or a combination. All right. The last section here is pretty straightforward. It's just the 5.7, and it's putting all of what we've done in chapter 5 together. We the how do we do the appropriate probability calculations, and how do we do the appropriate counting calculations, counting technique to use. So we're going to cover both these, and these are summary trees, which should help you in your study. Okay, so how do we determine the appropriate probability rule? Let's take a minute on this tree diagram, because it sort of guides us through how to do the right. And these green ovals are the end of the answer. Okay, depending on these questions, the yes nos to these questions, we end up with the right formula here. And we did lots of different formulas. Okay, we've done a lot of these different things. So if you are doing a single event, and that's a key thing, sometimes we're just getting a probability of a single event. We have the classical approach, okay? Or we also have the empirical approach, which is this one here. We talked about that. And then if we don't, so that's the yes answer to the question, is it possible to get empirical data? Empirical data means the outcomes are not equally likely. So are you finding the probability of a single event? Okay, yeah. So I'm finding the probability of flipping a coin, or rolling a fair die, or pulling a card from a deck. Those are a single event. Okay, so in those cases, we'd say, yeah, these are the single event probabilities. Are the outcomes equally likely? And if they're equally likely, that's the coin flip, that's rolling a die, and that's cards, is pulling a deck from the cards. So we can use what we call the classical approach and just count the number in the event space that we're looking at versus the number in the sample space. So if it's the probability of the event flipping a coin and having it turn up heads, the event of the head is one outcome. The number of outcomes in that event is one, and the number of the sample space is two. So the probability of heads is zero point 0.5. That again was the classical approach. Now, sometimes outcomes are not equally likely. And what we have to do at that point is, do we have any data associated with that? Okay, do we have any data that's been given to us? And sometimes we do. Sometimes we get data, and we had examples of this in the empirical section of the single event probability, which was where we started the chapter 5. We would just use the frequency of that event versus the number of trials. And that is, remember, it's frequency, it's the count of the event. And that problem set was just given to you. This is empirical data. This is observed data. This is data we have. It's not going back to equally likely, like a coin flip or a rolling of a die, equally likely events where we use the classical approach. This is where we're using data we observe. If we have no data, we just have to make a guess, and that's subjective probability. Okay. So those are the things we covered when we covered single event probabilities: classical, empirical, and subjective. But sometimes we're doing multiple events. Okay. And do the event, and that means no to this question of single event. What if it's, uh, what's the probability of flipping heads on a coin flip on the first trial and tails on the second trial? What's that probability of that? And that's why we ask this question: do the events involve or, and, or at least? If they involve or, we have to use the multiplication rules. And the multiplication rules relate to disjointness. Remember disjointness and mutual exclusivity? So if they're disjoint, the simple addition rule. If they are not disjoint, if they are overlapping in the event space, then we have to use the general addition formula right here. If the question involves and flipping a heads on first trial and flipping a tails on the second trial, then we use one of the multiplications. Okay. And it depends on independence. And remember that, keep straight the different definitions of disjoint and independent. And we use the two different we can use the simple rule for multiplication if the events are independent. If they're not, we have to use the general multiplication rule. And then of course, if you see the words at least, you have to use this kind of construct. As soon as you're in at least language, you have to use the one minus the probability of none, which is given usually in any kind of problem of this kind. So, example, deal or no deal. Here's the construct. 26 suitcases. They have 1 penny to $1 million in the suitcase, and the contestant gets to pick a case. Okay. So what's the probability that the contestant picks a case worth at least $100,000? Well, we've got to go to this table here to answer that question. There are 26 different suitcases, and these are the prizes in the suitcases. And 7 of the 26 suitcases have $100,000 or more. So we know the answer is going to be, by the empirical method, just choosing the probability of a single event. Remember, I'll go back here. If this is going to be a single event, just one case, are the outcomes equally likely? No, they're not. Can we get empirical data? Yeah, they gave it to us. They gave us empirical data, so we can calculate that. And so it's 7 divided by 26. That's the answer right here. And it's the empirical approach. Number of events that match the outcome and then the number in the sample space. So 27% likely to be $100,000 or more. All right. Okay. The probability that the contestant chooses a suitcase worth at least $100,000 is 27%. And we would say it this way. In 100 different games playing this game, we would expect about 27 games to result in a contestant choosing a suitcase worth at least $100,000. That's how we'd say that. Let's go on to another example. Which probability rule would I use? 14% of adult Americans have one or more tattoos. 50% have pierced ears, and 65% of those with one or more tattoos also have pierced ears. What is the probability that a randomly selected adult American has one or more tattoos and pierced ears? Remember, the key word here is and, so that's going to limit us to the multiplication rules. All right. So if we let T be one or more tattoos, and E meaning ears pierced. What we're asking for, what is the probability that a randomly selected adult has one or more tattoos, E here, T here, and pierced ears, E here. So we're finding P of T and E. If we go back to the table, we know this is not a single event anymore. These are two events, T and E, and we know it's and, so it's going to direct us to the multiplication rule. But we're not sure which one to use. Okay, we're not sure they're dependent or independent. Okay, so that's the first clause here. We need to determine if they're independent or not. But we have this here, and we did this in the last lecture. If the probability of ears pierced does not equal the probability of ears pierced given that you have a tattoo, one or more tattoos, if that's not equal, then we know they're not independent. Not equal, not independent. If these were equal, they would be independent events, and we could use the easier multiplication rule for independent events. In this case, we have to use the general rule. But thankfully, we've been given both these probabilities. Okay, we were given both these probabilities in the actual word problem, so we can just multiply them out. So here's what we'd say. The probability of selecting an adult American at random who has one or more tattoos and pierced ears is 9.1%. Okay. So now let's go on to our counting tree. We're on objective 2. We've done the tree that allows us to go through the right technique to use for probabilities, but now we have counts. Okay, so let's do this. This is our tree. We're going to end up with these different formulas here. Here are the formulas all over here. So let's go through the first step here. Are you making a sequence of choices? Okay. Yes or no? Does the arrangement or does the order of arrangements matter? Okay. And what we said here is that the combinations rule is you're choosing from n distinct objects, you're choosing R. And we have our formula for combinations. And we know for combinations, the order doesn't matter. Okay. And we're not choosing we're not choosing from a menu. We're not choosing one, then the other, then the other. Okay. We are not making a sequence. We're choosing R from a group of distinct N, both for permutations and for combinations. So the key difference between our permutations and combinations is, does the order matter? Okay. So sequence of choices is yes, the number of choices at each stage independent, okay, of other previous choices. If that's not true, you got to lay it out in a tree diagram. You just got to lay it all out and get to the right outcome. But if they're independent choices, this is the meal example here. Okay. And so this is where you would just multiply the P, Q, R, S, T, the number of choices at each stage of choosing a choice. That's the multiplication rule of counting. This is choosing from a menu of appetizers, entrees, and desserts. If you don't have the menu, you got to just lay it all out in a tree because you're making a sequence of choices, making choice one, then choice two, then choice three. Okay. And if they're not independent, you just got to try to figure it out as best you can. Okay. We did examples of this. This is where you 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 chose different I have to go back. The examples escaping me, but we had to list out all our choices because there was dependence on the issue. In other words, if you made a choice, you may not have been able to make that choice again. Okay, so that means you're pulling it from the pool, and this means non-replacement. If you're not replacing it, you've got to go ahead and use a tree diagram. So, does the order of arrangements matter? Well, no, we know this already. If order doesn't matter, we can use the combinations formula. If they do matter, we have to ask this: are you selecting all n objects or only r objects? If you're choosing from the whole group of n, then we have to get to n distinct, which we didn't do this problem here. So we don't have to worry about this. I should have put an arrow through this. We didn't do this problem, but we did do this problem. If all the objects are distinct and you're selecting all n objects and the order matters, then we're going to do the factorial problem. This is the problem of choosing the number of different ways the salesperson can travel through 7 different campuses. But permutations also means you're choosing R objects, only R objects from N objects. So remember what this formula means. N distinct objects. How can we choose R? And we know the order of arrangement matters. So hopefully that helps. Hopefully this diagram helps you make the right choices. Let's do a couple examples. So, which technique do I use? City Council, 5 men, 4 women. How many different subcommittees can be formed that consist of 3 men and 2 women? So we have subcommittees. There's a bunch of subcommittees, which is what we want to calculate. But how many different ways can we pick 3 men? And how many different ways can we pick 2 women? And these are going to go in order. Okay. These are going to go in order. And it's going to be got some similarity to uh, previous examples we've had. So there's a sequence of events here. Remember what we asked that. Is there a sequence of events? Select the men, then select the women. So we have the first times the second. Since the number of choices is independent of the previous choices, we use the multiplication rule of counting. In other words, we can treat this like the menu items problem. How many ways can we choose to pick 3 men? How many ways can we choose to pick 2 women? Like choosing 3 men from a group of 5 and then 2 women from a group of 4, if I'm getting that right. So the number of ways to pick 3 men from a group of 5 where order doesn't matter. Remember, order doesn't matter. We can use the combinations formula for each. If I have 5 men and I want to choose 3 without regard to order, I can use combinations, do this calculation, and it turns out to be uh, 10 is the answer. 2 factorial and 3 factorial. This is 2 and 5 times 4, that's 20. Because then we eliminate 3, we divide by 2, we get 10 for 10 different ways of, within a group of 5 men, choosing 3 without regard to order. We can also do the same for the women. put it into the combinations formula. But remember, this is also using the multiplication rule. It's like choosing the menu items. They have to go back to back, this one, then that one. So this is why we need to multiply one more time. Okay, I hope that's pretty clear. There's 60 possible subcommittees that contain 3 men and 3 women. So we use both the combinations formula and the multiplication rule here. One other in the Daytona 500, okay, 43 drivers in the race. How many different ways could the top 4 finishers occur? Now remember, order matters here already because we have first, second, third, fourth. So we're out of combinations, we're into permutations, all right? And we're not doing a menu. We're not talking about, one race, then another race, then another race. It's just one thing. Okay. It's not a sequence of things. Yes, there's one race, and we have to worry about first, second, third, and fourth. Find the number of ways to select the top 4 finishers. First way to do this is just to look at it and go, hey, at first I've got 43 choices. Then I have 42 choices, then 41 choices, and then 40 choices. That's a big number. That's 3 million different way, almost 3 different million ways to get the first order of the first 4. Okay. Remember, I have 43. Since the order matters, after I choose first, there's only 42 left to choose from, etc., all the way down to the top 4 finishers. So we could do it this way, just choose it this way. We also could do it the other way. We could do it using the permutations formula. Permutations formula is saying in a distinct group of 43, how many ways can I choose a group of 4? Okay, that's R here. With regard to order. I care about the order. So I use the permutations formula rather than combinations. I work this out. 43 minus 4 is 39 factorial. So I can eliminate 39 after 39 factorial. So it turns out to be 43 times 42 times 41 times 40, which is what we just figured out just by a rule of thumb. So permutations formula, the other normal formula, they both work. Any questions? That covers 5.5 and what we need to know for the course, and 5.7. Any questions among the folks who are here? Otherwise, the other folks, I will have this recording uploaded as soon as I can. Very similar to last week. And I apologize again. It's not it's not my desire to feel like crap here and not be able to join you in the lecture, but this is the best way to do it. I've had a rough 8, 9 days now, so I need to heal fast. I don't know what's going on. Any questions? Well, thank you for your time. Best of luck studying. We have our exams Monday and Tuesday, depending on your section. So we will see you next week. Have a nice weekend.